Hello, Borden.
Hello.
Hello, guys.
Hello.
Okay,
Hey, Dr.
let me see. I posted the homework early morning today. I did not post it on Monday, so I thought I will make the homework due on Wednesday. So that means that this will be the last homework. And we have the final exam on Monday, so less than 2 weeks from today. So the final exam will be online. I'll post, like we had midterm 2, I'll post it sometime before the exam, probably during the weekend, and it will be due on the day of the exam. So let's make it due by 4:45 p.m. So due uploaded during weekend. So basically, at least one of the problems will be a little longer in the sense that I will give some radiation problem where it will be very descriptive, though. I'll go walk you through the problem. Any questions? Okay. I want to carry on with the simple antenna we were talking about. I want to build on it, and maybe there's a chance that I might cut short on the discussion, and in that case, I will bring back the discussion on Friday. But I might also finish it. I'll see. Okay, let's do a small summary of what we were doing. So this is the idea of a simple antenna. And the idea is that we just have one simple length wire of length L. It is centered at the origin and it is on the z-axis. So its coordinates are x equal to 0, y equal to 0. And the top point here is at L over 2. And the bottom point is minus L over 2. So the length of the wire is L. It's on the z-axis. And our goal is to find the radiation somewhere, or the radiation field. Remember that it doesn't, even though we evaluate it at the infinite dome, the field itself could be there anywhere, right? So this is your radiation at some distance. R. So usually R is large. That's your angle. We have a current density in this wire, which is described by prime. T prime is z hat. So that's the direction of the current. It could be oscillating, so it could be going up and down. And that we characterize by I naught times, we said, just one Fourier mode. There could be a whole function of time here, any arbitrary function, but let's consider one Fourier mode, which is sine omega naught t prime. It's centered on the z-axis, so that's x prime, y prime, and we said this is a finite length, so we described it by a step function. Just fit in here. So it's minus L over 2 less than z prime less than L over 2. And this is how a simple antenna could work in a lab. If you want the electric and magnetic field, what we did say is that if you have R given this Z, what we will have is that the magnetic field will be perpendicular to this. So this is R cross Z. This will be, so magnetic field will be in this direction. And the electric field will be in this direction. And the magnetic field is given in terms of Js, and it is multiplied by C so that you have the units of electric field for the magnetic field that we write. So that's given as minus R hat crossed with mu naught over 4 pi, and there is a 1 over R. This means that this is a radiation field. Whenever we have a 1 over R dependence in the magnetic field, then you would say that's that's your radiation field. And we have here, what was it? we said this is equal to d cubed r prime and e by d cubed prime j r prime comma q prime. So that's just a way of writing it. Its dependence is given by the retarded time, which is t minus r over c. That's your straightforward retardation, but because of the geometry in here and the large r dependence, there is also a plus r hat dotted with r prime over c. So it should have been r minus r prime over c as a vector distance, but in the large R with respect to R prime, it's only the leading order that contributes. So all the angular dependence and the source dependence comes from mostly from this R prime dependence in this. We also said that the electric field, once we have the magnetic field, is just minus R crossed with electric field, also C times magnetic field. So you don't have to do too much work afterwards. The magnitude remains exactly the same as the electric field magnitude, and the direction is given by a cross product. So all these three vectors R hat, the vector E and B are orthogonal to each other. And that is captured by the relation. This is in turn equal to R hat crossed with electric field. Notice that one might conclude that, oh, so you have magnetic field is given by the top expression, and is also given by the third expression here. So there are two expressions, so one can actually peel out this term and relate it with the electric field. That's not true. So electric field is not really equal to this. And why is that? If you have, let's say, C times D is equal to R hat crossed with, let's put this as K. And then C times B is also equal to R hat cross E. Is that the same? That's not really the same. You can actually take an example and see. So for example, let's say this is R hat. Am I within the board? Yes, welcome. So that's your R hat. And R hat crossed with K, let's say K is somewhere here. So R hat crossed with K will be, and let's say minus, right? So that it's minus R. So this is your magnetic field. But any vector will, so for example, this is also, so this is K prime, let's say. K prime. That will also be equal to magnetic field. The angle doesn't really come into picture. It is the component of K that is perpendicular to this. So this is also equal to the same quantity. So this is K double prime. All these vectors actually will give you exactly the same. It is like the torque. If you want to calculate the torque, it is only the perpendicular component of the force that contributes to the torque, and all the lateral force goes to zero. So it's not unique. So simply because two torques are equal doesn't mean that the forces are the same. So that's a simple idea. I'll let you guys complete that argument. And with that small caveat, we actually calculated the power radiated. So we said, we argued that dp over d omega. Power is change in energy with respect to time, and that was equal to r hat dotted with electric field crossed with H, which was the magnetic field over mu naught. But we changed the cross and dot, r cross each c times b, so it is c times b dotted with b over mu naught. You can multiply by a c and a c, you get mu naught over c. So this was equal to c times b is given in terms of this whole quantity in there, and we calculated this and we showed that. Is there a simpler way of writing this? C times b. Let me write this as mu naught c over 4 pi and mu naught c squared. One more 4 pi and mu naught c over 4 pi. And that is 1 over r. So this is just so that I can capture all the constants in there, and that is an r square also. So the r square has been brought down, and this basically is, so power dp is equal to d omega over 4 pi times, when we divide this out, we have exactly the integral that is out there, mu naught c over 4 pi, that's your resistance, and the current is given by d cube r prime d by dt prime j. And squared. And we have to divide out by a speed of light c. That's the expression for the power radiated in the solid angle. So this will be called the angular distribution of the power. We calculated the quantity in the square bracket. Let me write that down. Refer back to last lecture's notes. Yes, so if we were to divide, after you divide out the mu naught and c, so what we are left out with is the power dp over d omega. So that's equal to yes, so this is mu naught c over 4 pi times, there was an r cross z that gives us a sine square theta, that's the angle coming in from, this is z hat and that's the r hat. That's the sine square theta terms, z cross r hat is sine theta. When you square it, that's sine square theta, and inside in here we have I naught square divided by pi, and that is cosine square omega naught t minus r over c, and angular dependence is mostly from the last expression I'm writing down, which is pi times L over lambda naught times cosine theta divided by cosine square. think I captured everything. Small points I want to point out here is, let's see. First is mu naught of C over pi. That's a constant, but that has the dimensions of resistance. So this is equal to about 30 ohms. And that's kind of a nice thing because it depends only on the vacuum properties, mu naught, speed of light, and 4 pi. So that's a resistance, and that is a current square. So that gives you the units of power, I naught square times R, and that's a constant. So we can say that's the amplitude of the power radiated. And rest everything has either a t dependence, time dependence, or an angle dependence. What does it depend on? The length L and lambda naught. What is lambda naught? We said this is oscillating with frequency omega naught. So that corresponds to a time period t naught, but so that's time period frequency mu naught, and mu naught times lambda naught is speed c. So you would say this is 2 pi over lambda naught times c. So lambda naught here is completely determined by how fast you oscillate this current with respect to time. So this whole angular dependence depends on the length L and lambda. Now, one thing is clear: what happens if this quantity was very small? If this was very small, sine of the small angle will be the angle itself, and you notice that the cosine theta will cancel out then. As a square of the sine, so cosine square theta cancels out, and the angle dependence is then straight trivial. So it is basically sine square theta, and that's the extreme approximation that is involved. Even later on, we will talk about the scattering, and that's an extreme where most of the details is lost. But here, since it's a simple example, we would like to analyze this a little more in detail. So let's see how we can proceed. Before we get into that, let's do one more thing, a formal feature, and that's what I want to do today, and that is basically the time dependence. It's a straightforward thing, but later on we will also go into the Fourier space, and we should have a clear picture of what do we mean by averaging time. So this is a time dependence, total time dependence in the sense, and this is coming as a square. Remember that whenever you have a squared quantity, if you average it, it doesn't have to be zero. Most often, when you average things out, there is a chance that you can get a zero out as a result. For example, if you have a positive quantity, negative quantity, and on an average, if it is random, then it is zero. But if it is a squared quantity, all the negative quantities get squared, and that's the idea of variance, right? Variance is always between zero and or it is always a positive quantity. So let's average over time. And why do we say it's okay? Because usually the frequency with which electromagnetic waves oscillate, especially in the visible region, is extremely high. The frequency with which visible light oscillates is about 10 raised to 15 hertz. So the nu omega is approximately 10 raised to 14, let's say 10 raised to 14 hertz. Very fast, and the wavelength associated is about 600 or 500 nanometers. 1,000 nanometers is about a micrometer, so it's about a half a micrometer, and the frequency associated with it is 10 raised to 14. So let's average that out. We don't get too much, we don't lose much information at all. So we have we can think of power as a function of time. to be. That is, let me say some constant c which has an angle dependence in it, and that is another cosine square omega naught t minus r over c. Whatever else is there, whatever else angle dependence has been captured in the angle of c. Let me call it a so that there is no c. A will come before now. I'll define my average power as integrate from 0 to time period t of the oscillations omega. So the time period associated with omega naught, so that's t naught, and dt over dt, and then again divided by t naught. That's a standard thing you do. Probably you have done this in AC circuits and many other places. That integration is equal to, it comes out 1 over t naught, 0 t naught dt, cosine square omega naught. So let me explicitly do that as cosine square of omega naught t minus whatever omega naught r over c is that. That's not time dependent. So as far as time integral goes, that's basically just a phase. So let me call that delta. So that's delta. Expand this out as an identity. Am I still in the space? Yes. So that's 0 over t naught dt 1 plus cosine of 2 times omega naught t plus delta. That's a half angle formula in trigonometry. And this can be evaluated, and the simple idea is that the second integral is 0. So the first integral is simply 0 to t naught dt 1 by 2 plus the second integral is 0 because it's an oscillatory term. That's exactly what happens when you have positive and negative quantities being averaged in a complete time period. This is 0 because the sign function goes from -1 to +1. But the squared quantity does not, and that's this 1 by 2 term. So this is equal to 0. Now that's not. That's a theta 1 over t naught 1 by 2, and this integral is just t naught. So that's exactly a contribution of half coming out from that. And we have otherwise got rid of or pretty much averaged out the time dependence out of the expression. So in that manner, our power radiated dP is now equal to d omega. I think earlier d omega was not written there, so that's d omega. and mu naught c over 4 pi. And there's a factor of 2 that has come up. So with that earlier pi, so I would write that as 2 pi in here. That's your resistant mu naught c I naught square. And I have sine square theta. So that factor of 2 that I got by averaging the time is put in here. And whatever is remaining is basically sine square pi sine theta over That's it. I think let me check if I missed any constants or anything. Let's see. Yeah, that's, and maybe I should also point out that this is the average power, right? So this is not P, so this is average power. So I have averaged out the power. Okay. Okay, good. So that's our expression, and now I want to analyze this. One thing is very clear. What if it is L is very small compared to wavelength? So let's go to the other side of the board. So what happens if L is very, very small compared to wavelength? In that case, since so that's L over lambda naught is very much less than 1. Since cosine theta is anyway less than 1, so this will be very much less than 1 also. If that is small, what we can say is that sine of pi L over lambda naught times cosine theta is pretty much approximately equal to pi L over lambda naught. So that's your extreme limit, and in that case, the power radiated, the average power over a solid angle is simply, let me put that whole thing as simply, so let me define 1 or mu naught C over 4 pi times I naught square as simply an amplitude of the average power, P naught T. So that's P naught T averaged out. So basically, I don't even have to write that P naught T, but that's emphasizing all the time. And what we have is sine square theta over 2 pi. That's it. And this and pi times L over lambda naught whole square. It depends only on that quantity. If I were to write it in terms of frequency, which is sometimes more common, like here, when you're talking in terms of the antenna, it is more common to talk in terms of wavelength. But if you were talking in another context where frequency was more relevant, you would also write this as P times sine square theta over 2 pi. Put in a 2 pi and a 2 so that you have omega naught times L over 2 square. So it tells you that it depends on the frequency square. But again, remember that this is all for L being very small compared to the wavelength. Very extremely large approximation. If that was the case anyway, but what is the total power radiated over all the solid angle? So if you were to add up all this, so if for each tiny d omega, you have this, add up the whole quantity. Can we calculate this? So let's do that calculation. So P of P total. So that will be equal to P naught T average, and we want to integrate this over 0 to pi sine theta, and then 0 to 2 pi d phi. That's your solid angle, and you have sine square theta over 2 pi and omega naught L over 2 the whole square. This is 2 pi, no phi dependence, so that's 2 pi and 2 pi cancels out, and what we have is, oops, the both space, move it out, okay. So that's equal to 2 pi cancels out, we have amplitude of the power as far as theta goes, the maximum angular dependence times, let me write it back in terms of pi L over lambda naught square. So that's taken care of, and what we have is 0 pi sine theta, sine square theta is there. Let me write that as 1 minus cosine square theta. If you remember, this was the same integral that came in the Larmor formula. So it seems like we are, this whole wire can be imagined to be a dipole in this extreme limit. And let's do this integral. So you do typically, in this case, cosine theta is equal to t. Cosine theta is equal to t minus sine theta, d theta will become dt. And the limits go from -1 to 1, then, or 1 to -1, and that is a negative sign. So when theta is equal to 0, so that's 1 to -1 minus dt. Oh, sorry, this is d theta. This was d theta, and now this is dt, and we have 1 minus t squared. And that integral evaluates to 2 coming from the first part, and the second part gives you 2 times 1 over 3, t squared over 3, so that gives you 1 over 3, and you, from both the limits, you get 1 each, so it's 2 over 3. So 3 times 2, 6, plus 2, 8 over 3. So we have the power permitted to be given completely by, and this is this could have been, if you had assumed this to be forming a dipole in the sense that this whole wire was considered as a electric dipole, or imagined to be a radiation from an electric dipole. In that case, this is all that you get. That's good, but now let's go a little further. We took the complete extreme approximation that L is too small compared to lambda, but let's now say that it is actually small, but we go a little bit not on the other side where lambda naught is smaller than L, but let's say L is just simply smaller compared to L. We don't make the extreme limiting scenario. So that is 10 minutes from now. Yeah, let me stop at this point because whatever remaining analysis is there, it will fit into very well in the lecture on Friday. I simply, so there are 2 cases that it will fit in very well on Friday. Today, I have to do a small thing that I have to take care of, and I'll use this 10 minutes for that. So I'll stop at this point. Any questions or comments related to the lecture? Is that clear? I abruptly stopped, but hello?
Yeah, we're good.
Yeah.
I'm good.
Okay. Thank you.
Excellent.
Thank you.
Yep. Have a good day.
Thanks.
Bye. Yeah. Bye.